Hey guys, welcome back to the channel. In this video, we will learn how to simulate the SRU process using Aspen Hysis. If you haven't already watched my previous video on SRU process, I insist that you first go and watch so that you can understand the process correctly before you start the simulation. Right, so let me just brief you through the simulation that is done here. As we can see, the entire process has already got converged. The process includes the Claus conversion process and also the tail gas treatment unit, which is the downstream of the Claus conversion process. So some of the plants, they contain only the Claus conversion. So let's first simulate the Claus process, and then we will study the results. And after that, we will design the tail gas treatment unit, and then we will converge them together, and then we will study the results of the entire process. So to begin with, we have the acid gas, which is entering the reaction furnace. Along with that, we have the air for combustion, and the reaction takes place inside the reaction furnace, and some amount of elemental sulfur will be produced along with unconverted SO2 and H2S present in the acid gas. So the liquid sulfur, the elemental sulfur will be condensed with the help of the waste heat boiler, and also it will cool the effluent gases up to a temperature of 300 degrees Celsius. And by doing so, a major portion of the elemental sulfur present in the furnace outlet will get condensed into liquid sulfur, and it will be collected at the bottom through the rundown. And the remaining uncondensed gases containing unreacted H2S and SO2, and along with some elemental sulfur, will flow into the first condenser, right? And in the first condenser, some amount of the sulfur present in the gas will get condensed, and it will be collected at the bottom. And the remaining uncondensed gases containing H2S and SO2 will be cooled up to a temperature of, say, 130 degrees Celsius. And before it enters the first Claus converter, the gases will be preheated with the help of this first preheater up to a temperature of about 230 degrees Celsius in order to provide the energy of activation to bring about the catalyst reactions taking place inside the converter. And here the remaining H2S and SO2 will get converted into elemental sulfur, and then it will again flow down into the next condenser. This is called the intermediate condenser. Here again, some amount of the elemental sulfur which is produced from the first converter will get converted into liquid sulfur, and it will be collected at the downstream through the rundown. And the remaining uncondensed gases containing the remaining amount of H2S and SO2, unreacted H2S and SO2, which is coming from the first converter, will once again be preheated with the help of this second preheater up to a temperature of about 210 degrees Celsius in order to carry out the catalyst reactions in the second Claus converter. Right? So the same thing happens. The elemental sulfur which will be produced in the second Claus converter will be condensed in the final condenser, and it will be collected at the downstream. And the gases which is leaving the final condenser is called the tail gas, and they contain negligible quantities of H2S and SO2. Alright, so this tail gas will be sent to the incinerator for SRU plants that don't have the tail gas treatment unit. But in this flow sheet, as you can see, that we have the tail gas treatment unit. So the tail gas passes through the TGT, which consists of the reducing gas generator. Okay, and from there, it moves into the hydrogenation bed, and then the gases are cooled with the help of this cooler, and then from there it goes to the quench column, and the gases are cooled down up to a temperature of about 45 degrees Celsius in the downstream of the quench, and from there it moves into the absorber and regenerator. So the first column that you see here is called the absorber, and the second one is called the regenerator. So the absorber overhead contains negligible quantities of H2S, and that is sent to the incinerator where it is completely oxidized to SO2. Okay, and the regenerator, the gases which are absorbed in the absorber in the rich amine will be recovered from the regenerator, and it will be recycled back to the reaction furnace with the help of this recycle. So I have added the recycle loop, as you can see, and all the gases will be returned back into the reaction furnace. Also, I have included the air demand controller, which will optimize the combustion air flow rate to the reaction furnace in order to enhance the process and maximize the conversion recovery. So we will see how we are doing this by adding the air demand analyzer in the tail gas, as well as how we are including the recycle into our simulation. Alright, so let's begin with the simulation, and we will start the simulation step by step. So to start simulating the SRU process, we need to add a separate property package which is called Sulsim, which is already available in your Aspen Hysis. So to start the first new case, just click on File, click on New Case, alright, and then click on Fluid Packages, and then click Add, and then select Sulsim, Sulfur Recovery. Right, so now we can see that it has added this fluid package, and it has included all the necessary components which will be used in the reactions for simulating the process. So all in all, it makes the work easy for us. And the next thing we need to do is we have to enter into the simulation environment. So then click on Simulation, and then a new window opens. In this, you select the second option, which is saying Start with a blank flow sheet. So click on Start with a blank flow sheet. Alright, so this is the blank flow sheet that opens up. Here we can't do anything, we cannot draw anything here. So we need to enter into a subflow sheet environment. For that, we need to double click anywhere inside this square. Alright, and then a dialog box appears. Here at the bottom, you can see there's a button saying Subflow Sheet Environment, and you need to click on that Subflow Sheet Environment. Alright, so now we have entered into the subflow sheet environment. Here we will be simulating our process. Alright, so to design the flow sheet, we need to add what is called the model palette window. To do that, just click on View and click on Model Palette. So the model palette appears. This model palette contains all the necessary equipments which will be used to design the layout of your SRU plant. Now we are going to add the streams. Click on this. Name it acid gas, or name it as wet acid gas. Specify the conditions, say about 50 degrees Celsius, and the pressure about 1 bar, and the flow rate is about 2800 kg per hour. Right, and then it says at the bottom, it says unknown compositions. So for that, we need to specify the compositions. Click on compositions, and then click on edit, and then here we need to specify the composition of the acid gas. Say H2S is about 52%, carbon dioxide is about 34%. Click normalize. Okay, so now we see that it has got converged. Next, we need to add the saturator. Feed stream is your wet acid gas. Include moisture to the stream, say W1, and the product stream as acid gas to preheater, or you can say it as acid gas outlet. Alright, so the thing has got converged. Actually, the purpose of adding the saturator is because Aspen Hysis will define the compositions on dry basis, but in actual, the streams are actually saturated. For that, we need to add the moisture at given temperature and pressure, and for that reason, we are making use of this saturator. Right, so at the downstream, we need to add a mixer. Actually, for this process, as I said, we will be adding the recycled gas. So we will recycle the gases which is coming from the regenerator overhead with the help of this mixer. So click on that and specify the inlet stream and outlet stream as acid gas to preheater. Alright, so now it has got converged. So actually the acid gases will enter at an inlet temperature of about 50 degrees Celsius, and it will be preheated with the help of a preheater up to a temperature of 280 degrees Celsius. Alright, so next thing is that we need to add the combustion air. Okay, let's continue with this acid gas line before we can add the combustion air. So as I said, we need to include a preheater here. So click on this heater and the inlet acid gas to preheater. Specify the energy as say Q1 and the outlet as preheater outlet. Or acid gas preheater outlet to avoid confusions. Okay, and then it says unknown delta P, so we need to specify something in the parameters. So click on parameters and in delta P you can specify something like 0.01 bar, and then we need to specify the outlet temperature of the preheater. So click on worksheet, and here the temperature you can specify it as 280 degrees Celsius. Okay, so now we see that it has got converged. Next we need to add the combustion air stream. Same like before, click on the saturator, say wet air, add the moisture stream, say W2, outlet as dry air to preheater. Okay, so at the bottom we can see that the temperature not specified. What we need to do is we need to click on conditions. We need to click on, alright, just close this window and then come here. We need to specify the conditions of the air. So click on that air stream and click on specify the conditions. Say the air enters at a temperature of what, 40 degrees. So we'll say 40 degrees Celsius. The pressure is about 1 bar. And the mass flow rate is about say 2500 kg per hour. Then it shows unknown compositions. Then we need to specify the compositions. Click on compositions and click on edit, and then specify the composition of air. Air contains 21% of oxygen by volume and 79% of nitrogen. So say oxygen is 21% and nitrogen 79, right? And normalize it and click OK. So now we see that the thing has got converged. And the next thing we need to do is we need to add the preheater, air preheater. So click on preheater, specify the inlet as dry air to preheater, specify the energy stream as the Q2, okay, and specify the outlet as combustion air. Combustion air to furnace, to reaction furnace, RF. Okay. So it says that unknown delta P. So we need to specify something in the parameters. Click on parameters, click on delta P, say 0.01 bar, and click on worksheet. And we need to specify the outlet temperature of the preheater. This is going to be about 350 degrees Celsius. So now we see that it has got converged. Close the window. Okay, what we will do is we will push this thing upwards because to make the flow sheet look simple and clear. Select all this and push it upwards. Okay. Alright, so the next thing what we need to do is we have to add the reaction furnace. So click on the reaction furnace, the first one, single chamber reaction furnace. Click on that. Specify the inlet gas as acid gas, preheater outlet, and the air stream as the combustion air to reaction furnace, and the outlet gas as RF outlet, reaction furnace outlet, RF outlet, OL. Okay, so we see that it has got submerged. Close the window. Let's make it smaller. Okay, now it looks clear. The next thing we need to do is we need to add the waste heat boiler, because the reaction furnace outlet, the temperature is going to be about 1100 degrees Celsius. So we need to add the waste heat boiler. So click on the single pass waste heat exchanger. Right, now specify the inlet gas as a RF outlet. Add the energy stream, say Q3, and then the outlet gas as waste heat boiler outlet. And the elemental sulfur which is produced in the reaction furnace will be condensed as liquid sulfur. So call it as LS1. Okay, now it says unknown delta T. So what we need to do is click on a worksheet and specify the, no, we need to click on parameters and say specify the delta T as say 0.01. Okay, now the thing has got converged, so you can close this window. Right, so the elemental sulfur which is formed in the reaction furnace will be condensed in the waste heat boiler, and it will be collected as liquid sulfur. Right, so the outlet of the waste heat boiler, the temperature is going to be say about 330 degrees Celsius. Right, so and the outlet of the waste heat boiler will contain the remaining unconverted H plus and SO2 present in the gas, so it will be sent to the first Claus converter. Right, so what we need to do is we need to add a condenser here. So click on condenser. So the inlet will be the waste heat boiler outlet. This will be the outlet gas. The outlet will go to the first preheater. Some amount of elemental sulfur will be condensed and collected at the bottom. So call it as LS2. Specify the energy stream, say Q4. Now it shows unknown delta T. So what we can do is click on worksheet and specify the outlet temperature of your condenser outlet gas, say 130 degrees Celsius. Okay, now it has got converged. So the outlet of the first condenser will go to the first preheater. So we will add the first preheater here. Click on heater and click the inlet as to first preheater. Specify the energy stream as say Q6. And the outlet of the first preheater will go to converter 1. Converter 1. Call it as converter 1 inlet. Or converter 1 inlet. Okay. Specify the delta P as 0.01 bar. And specify the outlet temperature of the first preheater, say 230 degrees Celsius. Okay, now we see that it has got converged. Okay, now what we need to do is we have to add the first Claus converter. So click on catalytic converter, the inlet gas as converter inlet, and the outlet gas as converter 1 outlet. It says that it is not solved, so we need to check if we have missed something. Okay, so it has got converged on its own. Never mind. Next, we need to add the condenser at the downstream. So add the condenser here. The inlet will be the converter 1 outlet. The outlet gas will go to the second preheater. Second preheater. And here again, some amount of elemental sulfur will get condensed as liquid sulfur and it will be withdrawn at the bottom. Call it as LS3, liquid sulfur 3. Specify the energy stream, say as Q7. Okay, go to parameters. Specify the outlet. Now, instead of specifying this, you can go to worksheet and specify the outlet temperature as 130 degrees Celsius. Okay, it has got converged. Just align it so that it will be clear for drawing the layout. Alright, so the outlet of the second condenser will be the inlet of your second preheater. So we need to add the preheater. Specify the energy stream as say Q8. The outlet to converter to the second Claus converter. Okay. Specify the delta P as 0.01. And specify the outlet temperature, say the temperature will be 210 degrees Celsius. Okay, now it has got converged. Now we need to add the second Claus converter. So click on catalytic converter, same like before, click on that. Converter 2, and this will be your converter 2 outlet. Okay, it has got converged. Close this. And then once again we need to add the final condenser. Click on condenser. And same like before, we need to specify the outlet of the final condenser is called the tail gas. Same like before, some elemental sulfur will get condensed and collected here as liquid sulfur. So we can call it as LS3, LS4. Specify the energy stream, say Q9. And go to worksheet and specify the temperature of the tail gas as 130 degrees Celsius, 130. Okay, so it has got converged. Alright, so align it in order so that it will be easy for us to understand. Okay, just leave that. Alright, so this is the overall Claus process, and we can see that the entire thing has got converged. So now we will study the effects, the conversion efficiency, and the simulation results. So this is your tail gas. Usually what happens is that, right, so we can start from here. The uncondensed vapors from the first condenser, which will contain unreacted SO2 and H2S, which is produced in the reaction furnace. So that will get converted in the first Claus converter, producing the remaining amounts of liquid sulfur, which will get condensed in the second condenser, and also it will contain some amount of uncondensed elemental sulfur along with unreacted SO2 and H2S present here. So once again, it gets converted into the inside the second condenser, inside the second Claus converter, and all that SO2 and H2S present here will get converted into elemental sulfur, and that elemental sulfur will get condensed and collected at the bottom of this condenser. So the gas which is leaving the final condenser is called the tail gas, and it contains negligible quantities of H2S and SO2, and also some amounts of COS and CS2. All right, so this is called the tail gas, and usually the temperature of the tail gas is about 130 degrees Celsius. So we can study the overall sulfur recovery efficiency by clicking on what is called the sulfur recovery unit. The tag on the top, you can see the sulfur recovery unit. Click on that, and then click on performance summary. Okay, so you have the performance summary of the individual equipment, the performance, the conversion efficiency in the thermal furnace, that is in the furnace, the converter 1, the converter 2. Okay, so the overall recovery efficiency of the SRU process is here. It shows 89.75. So we need to optimize this. So what we can do is we will add the what is called the tail gas analyzer in the tail gas line, which will adjust the correct amounts of combustion air to the reaction furnace, and that will optimize your stoichiometry, and that will enhance the efficiency of the process. Just like I said, this particular plant does not have the tail gas treatment unit, so we will just end till here, and we will show you the overall conversion rates, and then we will include the tail gas treatment process, and then we can converge it together, and we can study the overall recovery efficiency of the SRU process. So the tail gas here, first what we will do is this tail gas will go to an incinerator before it is sent into the stack. So we will add the incinerator here. Okay. So this is your incinerator, and the inlet gas will be your tail gas. And this is going to be, we need to specify the stream for combustion air to incinerator. Fuel gas to incinerator. And this is called the stack outlet. Okay, so we need to specify the fuel gas and air streams, fuel gas streams and the air streams. We need to specify it. Same like before, we will add a saturator here. Add the moisture stream, say W3. The product stream is already there. That's add to incinerator. Okay. All right. So we need to specify the conditions of the inlet air, same like before. Click on temperature, say about 40 degrees Celsius. Pressure is about 1 bar. And the mass flow rate is about, we don't know the mass flow rate, so leave it empty. Go to compositions and specify the composition of air. as oxygen 21% and nitrogen 79%. Normalize. Okay. And then specify the fuel gas composition. The temperature of the fuel gas is about 25 degrees Celsius. Pressure is about 3.5 bar. The mass flow rate is about, we don't know the mass flow rate of fuel gas. So we will specify the compositions alone. Right, so the composition of the fuel gas, click on edit and say methane 95%, ethane 4%, and propane 1%. Normalize. Okay. So we see that this thing has not got converged yet. So we need to study what's the problem. Okay. So the mistake was I had wrongly entered the pressure of the fuel gas as 3.5 bar, but usually it is not that much. It is around 1.6 bar. So I just changed that to 1.6 bar, and now we see that the process has converged. So we can close the window now. So this is the entire uh, sulfur recovery process, including the Claus process alone, as I said. Um, so now we will optimize the process by adding the tail gas analyzer on your tail gas line to enhance the conversion recovery process to optimize the simulation. Alright, so here we have the tail gas. So now what we are going to do is, as you see, once more, I will click on the model summary. Okay, so this will take you to a page where it will show you all the material balance of each strains, right? And this is the overall material balance for the entire plant. So you can check for the individual stream by clicking on the tags on the top, like it says feed stream or product stream, sulfur condenser, catalytic converter, etc. So if you go to what is called the performance flow sheet, there we need to study the overall sulfur conversion efficiency of the plant. So click on, where did it go? Yes, come here. Okay, so as I said, we need to study the overall sulfur conversion efficiency of this plant before and after adding the tail gas analyzer. So first we'll verify what is the overall sulfur conversion efficiency before adding the tail gas analyzer. So click on this sulfur recovery unit, alright, and then click on the performance summary results. So at the bottom, if you come at the bottom, you can see this overall recovery efficiency. So just drag it to the end of this. So you see that it is 89.75%. So so it means that it is not very good. So we need to optimize the process. So what we will do is we will add the tail gas analyzer here. So click on this tool ADA. It means the air demand analyzer, right? So the sample stream, click on sample stream and call it as tail gas. Specify the target variable as H2 to SO2 ratio. Now usually when you are running the plant without TGTU, the ratio is 2 moles of H2 and 1 mole of SO2. So we can specify the ratio as 2:1 or 2. Okay, then adjusted reaction furnace. This is the end of the loop. So click on furnace. Okay, so now it shows a consistency error has occurred. So what it means that we have over specified the variables, and the target variable that has been over specified is the combustion air to the reaction furnace. So we will go and make the changes there. So the reason is we have already specified the combustion air flow rate at the beginning of the process. Now we are adding the air demand analyzer, which will optimize the combustion air to the process. So in that case, it has caused an overspecification in the number of variables. So we need to correct. Click on this is the air loop. Click on this, right? And we have specified the mass flow rate as 2,500 kg per hour. So what we will do is just delete that. Okay. Close this. And then now the simulation process is on hold, as you see on this button. So click on active to run the simulation again. Okay. As you see that now the plant is not properly simulated. It has stopped the simulation until this part. Only this part has been simulated, and sorry, only this part has got converged and the remaining plant is not converged. So we need to make some adjustments. Click on this. What I did is I clicked the furnace model as thermodynamic, and I will change it back to empirical model. Right, when we do that, we see that the process does not get converged when you select the empirical model. So what I did is I just selected the furnace model as thermodynamic. Close this. Click on the air demand analyzer one more time. And we need to adjust the ratio. Say 4:1. Now change it back to 2. Sometimes it's frustrating like this, so it gets stuck up in between. Alright guys, so now we see that the entire process has got simulated. So we were stuck up somewhere in the middle. We don't know what was holding on. So what I did is I just changed the acid gas feed from 2800 kg per hour to 3000 kg per hour, just to give a bump to the process, just to bump the simulation. So by doing that, we completed our simulation by converging the entire Claus process. So now we will study the overall conversion efficiency. So click on Sulfur recovery unit, and then click on performance summary results, and come to the bottom, and at the end we can see that it is 96.22%. So the recovery has got optimized by adding the air demand analyzer in the tail gas line. So alright guys, thank you so much for watching this video. If you have any doubts, please comment down below, and don't forget to subscribe to the channel. In the next part of the video, we will design the tail gas treatment unit, and then we will converge the process together, and then we will study the simulation results. So thank you very much for watching.